this next problem, I feel like it's pretty straightforward. Okay. As always, the way I like to start my problems, I like to write my knowns and my unknowns. All right. So if we read the problem, the inner and outer surfaces of a 4 meter by 7 meter brick wall of thickness 30 centimeter and thermal conductivity 0.69 watts per meter kelvins are maintained at temperatures of 26 and 8 degrees Celsius, respectively. So our job is to determine the rate of heat transfer through the wall, and our units need to be in watts. Like always, you have to keep track of your units. Okay, so here's the wall. One side is 26 degrees, on the other side is 8 degrees Celsius, and the thickness between them is 30 centimeters. Okay, so as I write what I'm given, I'm gonna start converting units from centimeters to meters, degrees Celsius to kelvins, and also doing the areas as well. So let's get started. First thing that we're given is this 4 meter by 7 meter. I already know that that's gonna give me my area, so I'm just gonna write area is equal to 4 meters by 7 meters, which is 28 meters square. Okay. The thickness, or L in this case, is going to be 30 centimeters, but I want that to be in meters. So I just go ahead and divide by 100, which is going to give me 0.3 meters. Okay. Next thing that I'm given is the thermal conductivity, which is equal to 0.69 watts divided by meters Kelvin. Okay. Now, the whole degree delta t, which delta t. One thing that we've done is that we add 273 to convert it from degrees Celsius to kelvins, and when we subtract them we still get the same answer. So what I'm going to do, I'm just going to do delta t is equal to 26 minus 8, which is going to equal to 18 kelvins. Now keep in mind, again, this is in degrees Celsius. If I add 273 to 26 and 273 to 8, I'm going to get bigger numbers, and they're going to be in kelvins, and when I subtract them I'm still going to get 18 kelvin. So I'm just going to leave it as that, just for the purpose of time. Okay. Now, I'm being asked to determine the rate of heat transfer. Notice this here, rate. Okay. I have several different formulas for the rate. I have the rate is equal to Q over delta T. I also have Q equals to M dot. Well, I'm not gonna worry about that right now. Let's just get into this problem. I don't want to make it too long. I also have thermal conductivity times the area times delta T over the thickness. Okay. Now, let's start plugging in things. What I wanted to do, I wanted to write all the formulas, but we don't need this. We're not gonna use that one, right? Since I'm giving this guy thermal conductivity and the thickness, and I'm gonna use this one because I have the thickness in here and thermal conductivity. Okay, that's the formula that I need to use. This is a plug-in problem, so let's just do it. So the rate of heat energy transfer in this case is going to be thermal conductivity, which is 0.69. Don't forget your units, watts divided by meters Kelvin. My area, which I already did, is 28 meters square. and then uh, the difference in temperature is 18 kelvins divided by the thickness, which in this case is 0.3 meters. Okay. Now, some of you guys might be asking yourself, does it matter if I put a parentheses or does it matter if I put brackets? No, it does not. It doesn't. Okay. Let me start canceling things out. Okay. Kelvins, they go away. This meter goes away with one of these ones. Okay. Remember, meter squared means that you have two m's in there. So one of them cancels out with this one. And I'm left with one more m, which is going to cancel with the one at the bottom. Okay. So my final unit is going to be watts. Okay. Notice how everything cancels out. I am not forcing my units. I'm double checking that everything's canceling out. So if I do this, all I have to do is just multiply everything out. 0.69 times 28 times 18, whatever I get from that, I have to divide by zero point 0.3. Once I do that, what I'm going to get is going to be 1159.2 watts. That's going to be my answer. Okay, and that was it. That's pretty simple. Okay.